system operation and control purpose. And then we'll discuss about the blackouts and how these blackouts can be avoided, can be managed through this wide area measurement systems, single phase system. So that is how I have planned my presentation. Of course, some basics also are there, but I will be very brief on that. I hope my audio is clear. Audio and video.
Yes.
Yeah.
Yes.
Yeah. Okay. Thank you. So we know that we operated these power systems in a traditional way. Started with generations and then transmission, distributions, and consumer. That is how we're feeding the consumer. So one way of electricity, and the money was flowing in the opposite way. We know that. And now we are talking of the smart grid. We are talking of the future grid. Of course, there are many threats connected to this. There are many attributes of this, but basically, here we are encouraging the two way of electricity, as well as information, as well as money. And these technologies which have come up in last 20-25 years, like communication technology, ICT, and then signal processing technology, the power electronics technologies, smart materials, renewables. So all these technologies are pushing our power system to put more smartness in the power system. And it's a beauty of power system also that it is open to accept the new technologies, the new changes, right? So the all new algorithms and the new technologies are being very well used by the power system professional effectively for the operation of power system. We know that our generation is little bit now shifting. It is shifting from the fossil-based power station to the renewables, and as the advancement in material is going on, it's facilitating us to go for higher and higher transmission voltage, and to construct a big transmission line, and to have a big tie-up of the entire system. Solar is and wind is coming in big way, and this solar, thermal, and photovoltaic, they are coming in a big way, and that is how the generation side there is a paradigm shift, and this is putting the power system engineers to think more from the control and from the protection and from the operational perspective. At the same time, although we are going for integration, but we are also being doing some attempt in forming a small grid, which we call it as the microgrid. And this microgrid are based on the local generation, available generation, maybe from solar, wind, or any other dispersed generation, and then that is used for the catering the need of the local load, and surplus can be put in the grid. At the same time, whenever there is no generation locally, that time the power can be taken from the grid, and that is how the microgrids operate in grid connected mode as well as the standalone mode. And you know that these EVs, electric vehicles, are coming in big number, and all those vehicles will be connected to the distribution systems by some or other means. Maybe generation, maybe power they can take from the utility grid, or maybe from the microgrid, the local dispersed generation. So this is all happening in the power system, and this is possibly happening because of the development in power electronics, right? Power electronics is playing a very vital role, very important role, and it is facilitating us in connecting the renewables, in connecting some different form of load, etc., etc. And this microgrid you can connect, or this even your mobile charger, take it from mobile charger to your car, you can connect to the grid. And that is the beauty of the power electronics. So power electronics, we have now this voltage source control technologies, and with PWM techniques and all, uh, practically it is possible to, I mean, generate the current waveform and voltage waveform as you decide, right? So this wind or solar or the micro turbine or the fuel cell, right? These all are connected to the grid or to the microgrid through power electronics converters and inverters. So uh, it's fantastically helping us uh, for putting more smartness in the grid. We are not talking of the zero impact, net zero net impact. That means whatever we want to consume or whatever is your need, that we wanted to generate locally, and uh, over the period of time we expect that the impact of of a house or the impact of this load will be zero, right? So it's some sort of energy Swaraj. Uh, uh, yeah, of Professor Solanki. And its technology is also facilitating us. Government is also encouraging this, and that is good thing. So the point is, sources of electricity are changing from large fossil fuel to the dispersed renewable energy sources. So we are now taking as much power as possible from the renewable, and those are distributed. And secondly, the users, which we were earlier treating them as a consumer, now they are also taking part in production of the electrical energy, and this is all possible with the what we can say, the billing and the metering facilities and all. So the users of electrical energy changes from purely consumer to producers and consumers and managers also of the electricity. And this is something similar to that of the internet, right? It's something similar to that of internet. So when you are talking of the high voltages, then because you are getting you are availing this large SIL, and that's facilitate transmission of large power. But at other side, your X by R ratio is increased, right? As the voltages increases, the X by R ratio increases, and this of course will create some problem, which possibly needs some compensation and all. This is the center where from these systems are controlled. So this is what is the smart grid constituent. I will not spend much time on this, and we are all now talking of the smart grid, and smart grid. These are the technologies which make the grid smart, and this is how the smart grid is different than the conventional grid. Uh, you can read it from the presentation or from the paper, right? Now we'll just quickly review some fundamental, and in synchronous grid, the synchronous machines are interconnected through the large distances transmission line, and the power flow depend upon the relative angle between the rotor position, which we call it as the voltage angle, and we assign delta. And the frequency in steady state, when the grid is in steady state, we say that the frequency is same, right? So the electrical speed of the generator is same. And in asynchronously connected system, we have the HVDC system, where we can have a different frequency and different phase angle also, and we can interconnect the two systems of different frequency. We know that. Uh, when it comes to the grid control, basically we are controlling the voltage and the frequency, and obviously we are maintaining the quality, reliability of the power, and above all, this should be a very economical kind of power available to the consumer. But there are some questions like what happened during the load generation balance disturb, right? So it's very true that in a synchronous machine you can get the uh, you can use the inertia, which play important role in maintaining the synchronism. But what if the renewable is there, and because you don't have any rotating part, right? So this is what I was saying, that the voltage, if these voltages are maintained to nominal values, then it is the angle difference between these two voltages which play a role in transferring the power. So three-phase power is constant for the balanced sinusoidal steady state, and it is controlled by the phase angle, and that is how this phase angle comes basically from the rotor position, this rotor position, and it's closely related to stability. I'm sure that we had a session on stability, power system stability with Professor Doshi, and you must have touched upon many aspects of the stability. So when it is the system, interconnected system, we can have analogy of multi-machine system, something similar to this, and this generators, you can treat it as a masses, large masses, and uh, this are connected, and power system exactly behave like this. It's a spring mass system. So you can expect the swings between these masses, relative swings between these masses, and the oscillations between the generators pertaining to the same power station. We call it as the intra-plant oscillations, and there can be oscillations between one generating station and the other generating station, and these are called as the inter-area oscillations. And if these oscillations are not maintained, there are various reasons for these oscillations, right? And but the point is that if these oscillations are not maintained, then it becomes difficult to keep both the systems in synchronism, or to run both the systems in synchronism, and uh, at times your systems can go out of synchronism. So these are some of the graphs which are showing the loss of synchronism, sudden loss, sudden load thrown off, sudden generator. Uh, it's all, I mean, we study this in undergraduate course. And coming to the asynchronous link, we have HVDC, and this are connected with the converters, like one acting as a rectifier, another acting as an inverter, and power flow can be controlled by these converters, firing angles, and then other controllers. And these links can be I mean can be embedded to the existing system, right? So I will not go through that where it has to be used and what are the advantages and disadvantages, but this is what I was talking of. When you have a HVDC link embedded in a conventional AC system, then this HVDC link uh, can control the power over this transmission line, and it can also control the power over the AC line, because some of this power is what is being transferred from this area to this area, or from this area to this area. So the point is that the HVDC link, when they are embedded in the existing power system, that time we use this HVDC link for interconnecting two systems of different frequencies and bulk power transmissions and all that. But basically, it also facilitates the power system engineer to control the power flow, right? Because inherently, the AC power systems, once constructed, it cannot be controlled. It is not flexible, right? Unless you have some controllable devices put in the system. So that is what it's the facilities. We know that we have this HVDC link, and in Maharashtra we have this Chandrapur to Padgi HVDC link, plus minus 500 kV, and yeah. The another technology which I know I have a session, I know there is a session, is the facts, and this facts is again the application of power electronics to the power system. So these facts devices are uh, using the power electronics technologies control the power systems, AC power systems in real time, right? So it is possible because the power electronics technologies, the converters, inverters are generating the desired voltage and current at very fast rate, at very fast speed, and the thyristor-based facts. And there are the different kind of facts controller. The thyristor-based facts controller, which basically house the static valve compensator for shunt compensation, and thyristor controls series compensation for series compensation, and voltage and voltage source compensation. For voltage source compensation, we have the static synchronous compensator STATCOM, and then the static synchronous series compensator again. So both of these, the static synchronous compensator STATCOM and triple SC, these are the series controller. But the combination of this static valve compensation and this STATCOM, uh, uh, sorry, the combination of this STATCOM and triple SC gives birth to the uh, hybrid controller, which is very popularly called as the Unified Power Flow Controller, UPFC and IPFC and all those. So basically, all these controllers help you in increasing the power flow limit, uh, and then managing the damping of oscillations, managing the transient stability limit, etc., etc. And there are a variety of various families, various facts controllers, and they are used for certain purposes. So I mean, the point is that with the facts technology, you can make the existing AC technology a bit flexible, and many control problem you can solve. You can compensate for the distributed parameters like inductances and capacitances, and it also help in control, and it also help in what you can say increasing the transmission system capability. So this is the SVC, a very famous device. We connect it into shunt, and capacitors are put it in a switch mode, and it's the inductor conduction is controlled through this anti-parallel switches. One operate in positive of cycle, another operate in negative of cycle, and there can be various capacitor bank, and then there can be various values of inductances put in the controllable mode. And we know that if the line is loaded below the SIL, then the line is subjected to the over voltage, and if the line is loaded above SIL, the line is subjected to under voltage. And this device support is because basically because of the change in the reactive power generated by the transmission line, right? And this SVC, with the SVC, we can absorb or we can give support to the reactive power of the reactive power to the transmission line, and we can control the reactive power, and finally we can control the voltage. Yeah, so this is a series compensator, and series compensator connected in series with the transmission line. Capacitor is put like this in series, and again the conduction is controlled of this inductor to protect this capacitor against the fault generated over voltages. The nonlinear device metal oxide resistor is connected across this capacitor, and yeah. Now the STATCOM is a device. So we will use some. We will STATCOM is a device which is basically a voltage source converter device, and this generate uh, the voltage by appropriately controlling the switches, right? And this generate the voltage which is of the same frequency and same phase to that of the line voltage, the utility voltage. And the magnitude of this voltage can be controlled by modulation index, and the phase angle can be controlled. Uh, Phase angle is I mean this voltage is in phase with this voltage. So when the current flows, which is basically based on the voltage difference of these two end, then that current will be quadrature in nature, and that quadrature in nature current can help us in maintaining or in controlling the reactive power. This is how the what is the principle of the STATCOM, right? And in triple SC, so instead uh, the VSI is used to inject the voltage in quadrature with the current. So this voltage is generated in by this converter, and that voltage is put in the series is in series with the transmission line, and that voltage is controlled. So DC source, if you connect a DC source here, or if you connect a DC source even here, then you can control the active power also, because active power can be pushed from this DC source to this. But if you connect a capacitor here at the DC end, or at this DC end, no source, only capacitor, then you can only control the reactive power, right? So DC source can control the active power, but capacitors connected at the DC side of the STATCOM or triple SC will only control the reactive power. As I said, that the hybrid power flow controller, which is UPFC. So this hybrid power flow controller is the combination of both, and you can put the control voltage in series with the transmission line, which has some phase angle and some magnitude, and that control voltage can control the active power as well as the reactive power, because this V of PQ control voltage, which you are putting in series with the transmission line, can have the active as well as reactive component. We will see little bit on power system control perspective. So we have a different places we have a control control parameters, and I will not go into this slide, very basic slide. We load the transmission line to its security limit, and the power flow can be controlled, because you need to balance the load and generation if you want to maintain the frequency. And this load generation and the line uh, reactances, that is the vibers, determine the power flow. You can reschedule the power flow by phase shifting transformers, or by the series compensators, or by the HVDC can be used. In fact, devices can be used effectively to have the power flow. So this is how the power flow in this transmission line can be rescheduled, right? And the power flow can be controlled. So provided you have HVDC link or the facts controller introduced in this. The reason I am telling this point is that all these facts controllers are putting some pressure on the power system protection engineer, and that is how it is to be looked into. So while going to the protection, we must understand that what is happening in the power system, and that is the reason. So anyway, I will skip this slide. We know you have a session. You had a session on stability. We have angular stability, frequency stability, voltage stability, and the devices which can improve the stability of the power system stabilizer, the HVDC and facts controllers, and likewise. So this is the voltage control tap changing transformer. The voltage of the generator can be controlled by the regulator excitation system, and the flows between the regions are in the frequency. When it comes to the frequency control, the flows between the regions are brought back to the schedule, and the frequency is brought back to the nominal value. So this is secondary control, and the generation and load schedules is adjusted slowly to confirm the economic objective. Then that is the tertiary. Economic objective is later. Okay, so this is already we have talked of, and when it comes to the steady state, we have this load flow solution, which is important for the power system protection engineer also. And the fault studies is more important in power system protection engineer also, because the protection system design and the protection system relay settings and circuit breaker selections and all that will depend upon the fault current. And the famous diagram, everybody want to operate these power systems in a normal mode. If the reduction in margin is there, then you can go in a power system may go in a alert mode, which is the insecure mode. If some limits are violated, then it goes in a emergency mode, and some heroic actions are required to take the power system from this emergency to alert and to normal. Otherwise, it may go in extremities, and then I mean the synchronism is lost, and then you will have to look at the restorative actions or restoration of the power system. So again, going from black start, right? So it's very important to operate these power systems in this normal mode. Normal mode. If margins are reduced, then it goes to alert, or if limits are violated, it goes to the emergency. So we need to operate the power systems in normal mode by load tracking and generator tracking, and then obtain the economic dispatch also. We do the security analysis. We run the load flows with the number of contingencies, full contingency list, and then if there is some violation, then you can prevent some violation from HVDC and facts like that. And dynamic security, we assess this we again assess this uh, security, so with the dynamic data, and again run for the full contingency, and that is how the dynamic security is assisted. So this where the fundamentals and little bit of overview of power system, which is required from the control perspective, which was from the control perspective and operation perspective. And this control and operation is again becoming very difficult, and that's why. So I am in the class, I will call you later. Oh, I am in the class, I will call you later. Sorry, sir. Yeah. So sorry for that. And these aspects are to be studied, and the power system is to be studied by the protection engineer to design the power system, to design the protection system, because now we are in an era of the numerical protection, and computers are being very well used, and I mean there are a lot of changes. And see, I mean the entire paradigm is now shifting. I mean it's not only the protection device, you have an intelligent device. We know the capability of the processors and all, and the beauty of this communication system. So we have a very intelligent device with us, and that can be used not only for the protection, but it can be used for other purposes, control and operation perspective, data logging, right, the report capturing and all that, and giving some alarm to the operators. So everything is now possible with the technology that we have at present. So we will now little bit take overview of the protection systems, and then I will go to the VAMs and then the blackout. So we know the reason why we have a protection, why we should have a protection system. It is very important from the equipment and from the personal perspective, human person perspective, and these protection systems are to be used by, are to be deployed, are to be have on the power systems. Every part of the power systems is to be protected for primary protection and also for the backup protection, which is the second line of defense, and it works when the power system, when the primary protection fails. So this protection, we know that in a protection system, the main device which detect the abnormalities or the fault is the relay, and then it gives the command signal or trip signal to the circuit breaker that it has to trip during the abnormal condition. So whereupon this protective devices like CTs, like relays, get the information of the power system, it is nothing but the CTs and PTs. So CTs and PTs are treated like the ear and eyes of the power system, and you get the information of the power system in the protective relay through these cities and PTs. So the primary of the cities and PTs are connected to the high voltage side power system, and at the secondary you get very low voltages and current, which are the faithful replica of the primary current. And this is very difficult in a sense that these protective devices should operate during the fault condition, and during the fault condition your currents and voltages are much deviated from the nominal value, right? So fault current we know is very high, and the voltages goes close to very less value, and during that condition your relay should get the fruitful replica of the current and voltages. Also, when the fault occurs, we experience the DC transients in the fault current, and these DC transients, high frequency transients generated will give birth to the decaying DC current, and it causes the city to saturate. Similarly, this subsistence transient are observed during the VT. I will come to the next slide. But the point is that when the city is saturated, then it doesn't give the accurate value or accurate replica of primary current, right? And that is how the relay get the wrong information during the city saturation, and it's very crucial that because your decision of the relay depends upon the information given to the relay. So the city saturation should be avoided. There are some techniques to handle this situation. Hardware saturation, hardware compensation, or the software compensation. But it's very well known that the power systems engineer normally oversize the city. Okay, normally oversize the city, and the oversizing of the city will definitely ask for the high cost of the installation, right? Because size of the city is you are expecting very huge. Coming to the CCVT, that is the CVT, that is capacitive voltage transformer, and CCVT, capacitive coupled voltage transformer. See, the point is that we need to reduce the voltage. The system voltage is very high, and that we need to reduce. So you can comfortably use the transformer, but the point is that using that transformer, I mean, you can think of the transformer where you are reducing the 440 kV to some 5 volt or 10 volt, right? So cost of the transformer will be very high, and that's why this capacitors divider circuit is used, and that is what is the CCVT. But the point is that when this capacitor circuit is used, there is a phase shift, and because of that phase shift, if you need to compensate that phase shift, so you need to put the reactor. Madam, lecture. You need to put the reactor. So this reactor is compensated, is used to compensate this CCTV and CCVT. But the point is that when this capacitor is connected to capacitor in combination with this reactor, will generate some sort of resonance, and that is called as the subsistence. That is called as the ferro resonance, and this ferro resonance generates some kind of subsystem oscillations. Okay, and the point is that, I mean, see, this is the fault voltage. These are all the simulated curves. This is also simulated graphs, and this is also simulated graph. So the system voltage is the nominal voltage, but when the fault occurs, the system is voltage drops, and as the system voltage drops, the voltage is, as the system voltage drop, this less voltages is to be informed to the relay, and because of this phase resonance, there is oscillation, there is a subsistence oscillation. So you can see that this is the actual voltage, but the CVT will give you the voltage something similar to this. And you can see that these oscillations are present for one cycle also, and protection decisions are now are to be taken within this one cycle, because otherwise your fault current is very high. The fault current is very high, right? This will damage, and that's why you cannot allow the relay to wait till damping of the subsistence oscillations. The subsistence oscillations are present for a very small time, mind well, and that is what is putting again the protection engineer in stress, because you are giving a wrong information to the relay, and the relay will maloperate, right? And that's what is to be. That's what the subsistence oscillations generated because of the phase resonance are to be handled, or are to be, I mean, addressed well, in order to have a good protection decision, correct protection decision. By the way, is there any question? Is there any question? I mean, shall we take the questions in between, or we'll wait till the session end? I can take the questions. So somebody should read me. Somebody should read for me. Yeah. Any comment and any listing? Not getting any feedback, so little bit. Hello, it's going fine.
Yes, sir. Yes, sir. If you can take it at the end, it will be good.
Okay, good. Thank you. So, from my end, I mean, I need some sort of feedback, little bit feedback. Okay. So we know that this relay, and this relay is take a decision of abnormal condition from the CTs and PTs, and this relay is nothing but a logic device, right? And it has some setting, it has some small setting, some small program, right? Now this relay, this CTs and PTs are something similar to ear and eyes of the power system, of the relay, right? Of the relay, of the protection system. And this relay, I mean, there is no, now we are talking of the protection, there is no change in the basic protection philosophy, but what is being changed over the years is the technology used for this relay, right? And this relay, earlier those were the electromagnetic kind of relay, because we all were playing with the electromechanical technology. Then we had the solid state relays, because then the solid state technology played its importance, and that was the technology. And now we are in third generation of the protective relaying system, and that is the numerical relays, where the processors are used, and these processors are used basically here. Okay, these processors are used here. So so we know that this numerical relay is basically look like this uses the microprocessor or microcomputer or DSP, and they look like this. So you have the microprocessor or DSP in where the ALU, the memory, the registers, etc. are there, and they take the current and voltage signal. Current signal is converted to the voltage signal, and this continuous signal, this analog signal, cannot be processed to the microprocessor or DSP, and hence these signals are converted to A to D with the help of A to D converters, and then the digital signals are processed here, right? So you are converting this continuous signal, analog signal, to digital signal, and then you are processing. Okay. We know there are some fundamentals which are to be studied and which are to be implemented, like we know the Shannon's criteria, the sampling theorem, that the sampling frequency should be at least twice, otherwise it will align with the low frequency signal. So this slide is showing you the fact that when a DC signal is sampled with, when a 50 Hz signal is sampled with 50 Hz sampling frequency, then it aligns to a DC signal. And then these sample signals are given, these samples are given, samples of current and voltages are given to the relay, to the processor, and in the processor there are some programs which works on computation of the phasor values. So they run some phasor estimation algorithm, and those phasor estimation algorithms are run in the microcontroller or in the DSP. And look at this. This is called it as the window of computation. So there are a variety of techniques of computation of these phasors, right? And those phasors are then used for the protection purposes. So phasor has two values, the magnitude and the angle, and these phasors are computed based on the previous data. So you can see here the window wherein you have collected the data of half cycle, and your computation of the phasors will be based on the data collected in the half cycle. So whenever the new signal comes, the last signal is being kept out, is asked to exit, and this window size is kept constant, right? And this is what is the moving window. So window is moving forward as the signal is advancing. And you can find that there are a variety of the algorithms which are being presented and which are being used, which are in use by the actual this relay. They uses the half cycle or the full cycle windows. So obviously for half cycle your computation time will be less, but for the full cycle your computation time will be more than that of the half cycle. But half cycle may gives you little bit of imperfect information, but in a full cycle window, as your complete window is enriched with lot of information, the full cycle window will accurately generate the will give you the phasor estimation more accurately. Now these are some of the aspects when you are you have a lot of issues, and still this area is open on computation of the phasors, computation of the magnitude, and then computation of the frequency also. People compute harmonics also. So because you can see that once you have a sample in, then you process the sample and you compute, right? The processor is with you. There are some hardcore issues when you are computing. See, you are not computing the phasors. You are, of course, computing the phasors in all conditions. I'm not saying that, but your phasor computations, you are in great need of the phasor computations, or more accurate phasor computations, particularly during the fault condition. And during the fault conditions, you can see your fault current itself is corrupted. It's not sinusoidal. Okay, your phasor computations will depend. Like if you can say this window 1 is enriched with the pre-fault data. Okay, the window 3 is also enriched with the post-fault data. Here there is suppose a fault, but your this window 3, okay, window 3 or window 2 is enriched with the post-fault as well as the pre-fault data. So you can expect the erroneous estimation of the phasors in this particular period. Okay, while in this period the phasor estimation algorithm will estimate the correct value of the phasor. So these are some of the hardcore issues, and a lot of research is being done in this direction also. So basically these phasor estimation algorithms are the fundamental frequency filters, right? So you estimate the phasors at the fundamental frequency. Frequency is an important information given to the phasor estimation algorithm, and the point is that the power system frequency is somewhat deviating from the nominal value. It's not always constant, and as we know that the power system frequency is varying, that correct information of the power system frequency is to be given to the phase estimation algorithm. Otherwise, your magnitude computation as well as the angle computation may be erroneous. So estimation algorithms can be viewed as the digital filters to extract a fundamental, okay, because you are estimating the fundamental frequency phases, and they are basically the harmonic filtering the frequency response of the estimation algorithms. Then after estimating the fundamental frequency in the relays and all, then the relay take a fundamental fundamental phases and fundamental values, and appropriate value I will say, because there is a lot of things which can be estimated. So appropriate values is of voltage or frequency or current is estimated, and the angle is also estimated. And then the relay take a decision, and then it gives to the circuit breaker. And circuit breaker is a switch where the actually we open the circuit. I will not go into the detail of the circuit breakers and all. Coming to the protection paradigm, as I mentioned, we have overcurrent protection, distance protection, differential protection. But now, in a present scenario, these protection aspects are being taken, protection decisions are being taken, the protection algorithms are being done in a numerical environment. Right. So this is a distance protection, which basically takes the current and voltage information, compute the impedance, and then if the impedance is beyond the set value, then you can say that there is no fault. But in case of fault, what happens is that in case of fault, suppose the fault is at F1, what happens is that the impedance computed by this distance relay falls below the transmission line impedance, and that can be treated as a fault, and the trip signal to the circuit breaker can be generated, and circuit breaker can be asked to trip. So this is how the distance protection works, and there are a variety of there is a family of these relays like impedance relays, Moho relays. I will not go into advantages, disadvantages, but now we are talking of the most stable relays, which is a quadrilateral relay. And this quadrilateral relay characteristics, earlier it was not possible, but now it is possible to realize and simulate because of the numerical environment. Because of the numerical environment. पाण्याची बॉटल. आणि चहा सांगितलं? सांगितलं नाही का? नाही सांग. Thank you. So frankly speaking, these characteristics of the numerical relays which we studied in undergraduate, and those books were restricted because of the technology, and it was difficult to realize some different characteristics. But practically speaking, now in a numerical relay, you can realize the characteristics as per your desire, because when it comes to numerical relay, it is just when it comes to numerical relay, then it comes to the programming aspect of it. Second philosophy is the differential protection, which basically works on the differential difference between the currents. Current differential is more popularly used, but of course the differential protection is there on the voltages, and then the power differential. Okay, so when it goes to the transmission line, you know that you cannot straight away compare this current. This current difference will not be zero, because there is a line charging current which comes from the distributed line parameters and all. And yeah, this is the slide showing the transient spectrum. So the electromagnetic transient and the switching transients coming into this time range below 0.1, and then the synchronous machine transient, synchronous machine dynamics coming in the range of the 0.1 to 1, and then the governors, of course, from 0.1 to 10. This is to the log scale, And then the frequency control and the boiler dynamics and all these are very slow nature of transient, but protection engineer has to work in this particular range. Okay, in this particular range. So protection time is relay time plus the circuit breaker time, and the protection time is less than even one cycle. So uh, so that is what are the hard constraint, because circuit breaker is a switch, and in the circuit breaker you have to physically interrupt the circuit, so that current is to be interrupted in the circuit breaker, and it is a mechanically operated switch, and that's why it's what we can say, its operations will be little bit sluggish. Okay, so it will take more time. It will take more time to operate than that of the relay. Yeah. We know that uh, to maintain the transient stability of a system, which is equally important, which may be hampered because of the fault, and to maintain its transient stability of the system, the speed of the relaying is important, right? So let's take this situation that the generator is supplying the power to the system over the two transmission line, and there is a fault on one of the transmission line, right? So in these situations, what you should do, you should isolate this transmission line as quickly as possible, and possibly you can then transmit some power over the healthy transmission line. So you can see here we have studied this case in equilibrium criteria, and you know that when the fault occurs close to this bus, your power goes to zero. Power transfer goes to zero, and then the generator accelerates because the power is not transferring. So you move from point B to C, and somewhere you have to open this faulty transmission line. So if you open this faulty transmission line, then the power flow will shift from this curve to this curve. Okay, this is the power flow P delta curve with both the line. This is the P delta curve with the single line, and that's why in this period the generators are accelerating, and in this period the generators is decelerating, and this accelerations and decelerations is area A1 and area A2. We study this case from transient stability perspective with that famous equilibrium criteria, and you will appreciate that the limiting case will be area A1 is area A2. Now the point is that this area A1 and A2 depend upon when this transmission line is being removed, when the faulty part is being removed, and the faulty part is being removed. That means this transmission line is being removed, and then this uh, transmission line, I mean the removal of the transmission line, operation of the circuit breaker of this transmission line will decide this where this point C is. And you can understand that if the protection is fast, if the protection system operation is fast, then this area can be reduced, and you have a more margin, you have a more safe margin to implement uh, to uh, to have your power systems in a transiently stable mode. So this speed versus time, speed versus accuracy is a very famous conflict, and in proper engineering decision is to be taken, because if you reduce the time, then your accuracy may be compromised. It doesn't mean that if you increase the time excessively high, you will get more accuracy. No, that is also is not correct. So yeah. So for the transmission line protection in the power systems, we are mainly going for the transmission line protection, distance protection, and the distance relay is most commonly used because it performs both the tasks, the primary as well as the backup. The primary protection should be as fast as possible without any intentional delay in the time, and backup protection should be responsible for providing the protection if primary protection fails, right? And we know that for the distance protections we have the multiple zone, and zone 3 takes care of the remote end, and there is a very wonderful paper on zone 3 setting by Professor Phadke, uh, the critique on zone 3, and zone 3 should not be ignored, right? Because the reason for many cascading failures and all that is the zone 3, and zone 3 is as small, is as slow as possible. I mean, sometimes people set it zone 3 for 80-90 cycles, like that. So it should take all possible conditions of the fault. So this zone 1, zone 2, zone 3, we know how to set it. Normally for this line, 80% is set to the zone 1, 120% to the zone 2, and longest line is the zone 3. And this is the impedance Moho relay. This is the Moho relay. This is the transmission line characteristics, zone 1, zone 2, and zone 3. Uh, these protective relays are very badly affected by what is being called as the load encroachment. So what happens when the load on the system increases? When the load on the system increases, this operating point, which otherwise would have been at this place in this particular region, goes traveling in this particular part. And if this operating point, uh, because of higher load, because of increase in the load, if it goes and stay for sufficient time in any of the zone, then that relay, then that zone may trip, because the relay put here is have some setting, and if this operating point is going and staying in this particular period for more time, then it may trip up that particular zone 3 or zone 2, and this particular problem is called as the load encroachment. Okay, this particular problem is called as the load encroachment. So load is encroaching the area of the relay, and you can go through these equations. We can derive that this impedance seen by the relay is V square upon P minus JQ. Okay, power flowing in this transmission line. The apparent impedance seen by the relay R for the steady state positive response model of the power system is given by this equation. Okay, and this depends upon this P and Q. Okay. So to avoid this, what is being done is that this particular part of the system, or this particular part of the relay, is being chiseled out. Okay, normally the normal operating conditions and the load has high resistance and the low reactance. So you can see that if the point is coming, the impedance seen by the trajectory, the impedance seen by the relay, or the relay trajectory is coming in this particular area, then it is being uh, then it is being seized, and it is this particular area is chiseled out, and the relay is not allowed to operate in this particular area. While if you consider the fault has the very low resistance, and you have a fault loop impedance. So if the fault is occurring, it will put the operating point in this area, and that is how the relay is block operating or mal operating from the load encroachment. Okay. The another point, or another way, another another thing, why the distance relays are maloperates, or why the distance relays are badly affected, is the power swing. Okay, so we are just little bit discussing the reason why distance relay maloperate. Then we can see with this numerical relays and with this synchrometer measurement how we can go for its prevention. So we know that because of the load generation imbalance, there are the active and reactive power oscillations, which are of low frequency, and they are considered, they are treated as the power swing. So it is a consequence of large system. Uh, it can be a consequence of low generation imbalance, sudden change, or it can be a consequence of large system disturbance, or the post fault phenomena. And the point is that all this power swing will be seen by the relay as an impedance swing on the RX plane, and for some time the if that impedance go below the stated value, then the distance relay may trip, and that is how the power swing affect very badly to the distance relay operation. So if the impedance trajectory stays in the relay zone for sufficient long time, then the relay will issue the trip decision. So this is the operating point. This is the transmission line characteristics, and these are coming from the generators. This is the generator. This is the generator at sending end. This is the generator at receiving end, and then this is one voltage, another voltage, and this is the relay characteristics. Okay, so this operating point during the power swing may travel towards the relay characteristics, and if it stays for sufficient time, then the relay may trip. Now, there's a peculiar phenomena that when this operating point comes like this and touches to this particular line, hits this particular line, uh, practically, I mean, at this particular point, the voltage is zero, right? And this is a transient phenomena. It cannot stay there for a long time because the system is oscillating, right? System is oscillating, and this is being called as the electrical center. This is being called as the electrical center. So at electrical center, certainly your relay will take it as a fault. Right? Your will take it as a fault. So obviously the system may lose the transient stability, but relay will have to operate. So I will not go through this slide in detail, but what it is showing is that if this you define this ES upon ER equal to K, and if K is greater than 1, you can plot the the trajectory goes like this, and for the another case, the trajectory goes like this. So we can see that. Yeah, this is what I was talking of the electrical center, that the electrical center, the voltage is zero, and the relay at both the end will trip the line. Thus the existence of electrical center indicates the instability in the power system. Okay, so these are hardcore protection issues. So the point is that this angle can give you the information that in which zone the impedance trajectory will hit. Okay, so if the impedance trajectory, but obviously if this impedance trajectory stays in the relay zone for sufficient long time, then the relay will issue the trip decision. खाली ठोसर मॅडमला पण जाऊन हो खाली जात म्हणजे ग्राउंड फ्लोर ना okay. So yeah, so these are some simulated voltage and current waveform, how these voltages and current look like during the power swing. You can see that during the power swing, of course, power swing is a transient phenomena. The system is under swing, and during the power swing, when voltages are less, then the current are high. Okay, when the voltages are less, then the current are high. So it may be this particular region, the impedance seen in impedance trajectory. But when voltages are less and current are high, this particular situation, the relay will take it as a fault, because voltage is less and current is high. So this current and voltages from the current and voltages using the power swing, we can very well see that the relay will trip on the power swing. So there is some intelligence to be provided to the distance relay so that it can block against the power swing, and that is how this power swing block set are put. They are nothing but in all the power set power swing block set. What relay does is that the relay monitors the travel time. Relay monitors the travel time from one location to another, from this one location to another location, from this one location to another location. And if this travel time is very slow, then they declare it as a relay, as a power swing, and the relay is not allowed to trip. Relay is put in a block region. On the contrary, for the fault, the travel time will be very small because fault is a fast phenomenon, right? And this travel time will be very small, and as the travel time is very small, then the then the relay is put in an unblocked zone, and the relay is allowed to trip. So this is how the faults are distinguished from the power swings are distinguished from the fault. This is also very busy slide showing the effect of this compensation. So let's take the series compensation. The line is compensated. Line is compensated by a series capacitor like TCSCs or the triple SCs and all. And this transmission line impedance seen by this relay will depend upon where this fault is occurring, and also it will depend upon what is the compensation. So what is the capacitor that is coming in the series? Yeah, I just had my tea. So the point is that when this XC is less than that of XS, where XS is the loop impedance, loop inductance, and XC is coming from hello. ते टॉक चालू आहे. मी करतो पण एक 1 तासानंतर. Sorry for that. So the point I was saying is that if this XC is less than XS, if this XC is less than XS, then this relay exhibit the voltage inversion. The voltage angle is inverted. You can little bit work out. You can little bit work out with. The circuit fundamental. Madam, नंतर काम करतो. You can work out with little bit with the circuit fundamental. Okay, and when this XC is greater than XS, then the angle of the current is inverted, and this also you can work out with the circuit fundamental. And these phenomena in the protection literature is called as the voltage inversion and current inversion. So these are basically coming, or these are basically happening because of the series compensation. And both of these inversion phenomena, that is the voltage inversion and the current inversion, are disturbing. Both of these inversions are maloperating the relays. So you can see that these are all again from the simulation exercise, that the voltage and current is being inverted, and this is putting the relays in a blind step relay are being maloperated. Okay, with this preamble of the protection, we will now goes to this blackout, and then we will go to the numerical. Then we will go to the single phase measurement. Any suggestion or any comment or any question on the part so far we have? So far I have gone through. Okay. So this blackout is a rare phenomenon. Okay, and this basically blackout means the loss of synchronism. Your power system is no longer uh, in synchronism, out of step, right? So generators are out of steps. So there are a lot of vulnerabilities, and this may be coming from the planning, from the control of the from the control system design, from the planning, from the insecure operations, from the hidden failures, from the inadequate uh, uh, special protection schemes like under frequency links and likewise. So uh, these are what the reasons why blackouts are being reported or why blackouts are being happening. It's a rare phenomena. It's a rare phenomena because the statistic shows that it's a rare phenomena, but its huge effect is very huge. Okay. The defect which themselves will not produce immediate action, but will remain undetected until some other system event occurs. That is called it as the hidden failure. Okay. Uh, so when everything is normal, they are undetected. They will not post their nodes. But if something is in stress condition, then they will show their importance, and they finally result in a blackout. So this hidden failure detection is a big task, right? And it's not so simple to detect the hidden failure. So blackout occurs maybe because of the system conditions. Okay, the nature of the system is synchronous, and because of the stress condition, outages may be happening, and proper control action may not be taken. Inappropriate action may be there, and the cascading this results into cascading failure, and this results into loss of synchronisms and okay. So because of the stress condition, there may be some outage, and inappropriate control action may not. I mean, the appropriate control action may not be there, and that is what may be resulting into blackout and loss of synchronism or the complete dark. So blackout cannot be, I mean, completely avoided. They are something similar to the accident, but they can be made less likely. And how they can be made less likely? They can be made less likely from by designing the power system to make it less with less stress, make the stress less likely. Obviously, the random events are beyond your control, but you can certainly put more intelligent devices for the control purpose and for the sensing purpose, and you can collect a lot of data, and that data can be processed, and that can be used to predict some abnormalities, some abnormal conditions, and appropriate control actions, early control actions can be initiated with more intelligence kind of control and all. So that is what the blackout, that is what we can do. So let's go for the ductile system, not the brittle system. Okay, the brittle system certainly will break with a disturbance, with the impact, but the ductile systems will take the impact easily and reduce its bad effect. So the main operational controls we have connected are the high-speed controller and protections, and see this high-speed protection equipment autonomous for the for speed, and if they are put in very large number, then possibly we can I mean we can minimize the occurrence of the blackout, if not completely eliminate it. So high-speed wide area measurements will play the important role in that, and the important system. Hello, the important system which the important technology which provides or which assures this thing is the wide area measurement system. So this wide area measurement system is assuring the power system engineers a lot of things, and it helps in putting a more smartness in the grid. And obviously it's not new. And quite a substantial work has been done in the wide area measurement system, and it has been successfully deployed on many power systems, and it is working faithfully. So these wide area measurement systems, WAMs, basically we are interested in the phasor value of these two locations. Okay, and the phasor values of these two locations, you can go with the difference between the phasors, maybe angle or maybe magnitude, for different applications. Like for stability purpose, we will be interested in angle difference. But for differential protection purpose of a transmission line, let's say, we will be interested in the phase as well as the magnitude difference, the phase angle, the phasor difference, right? So what is done here is that it's, as I said, it's has been discussed quite a lot now. These two signals are measured with the same time tag, and this time tag signal is taken from the GPS. Okay, so these two signals are measured with the same time tag, and time tag is taken from the GPS, which is common to both the location. So synchronizing pulses are obtained from the GPS, and the clock is same, and then those DSPs which compute the phasors are put here. So those are called it as the PMU. Okay, so those are called it as the PMU. PMU stand for phasor measurement unit, and this phasor measurement unit is in the phasor measurement unit, it takes the signal from CT and PT, and the time signal it take it from the GPS, and then this is the hardware, the microprocessor or the DSP compute the phasor value, and then it is available for the communication port, right? So sampling rate should be as high as possible. Of course, it will depend upon your applications, and this signal, this GPS signal, time signal, is global, is common. Professor Phadke is the inventor of this phasor measurement unit in Virginia Tech, and I mean, I had a chance to interact with him, and when I asked, so he replied that he thought of only state estimation applications while he was developing the PMU. But now you can see the PMUs can be used everywhere for every applications. Via transmission, we are now talking of the distribution system PMUs, micro PMUs and all, and it's not now difficult with the available DSPs and technology. We can build a PMU in the UG lab. Okay, so in this PMU, this, as I mentioned, this data of the half cycle and full cycle is processed, and then this data is then the phasors are computed, and those phasors are then made use for the protection purpose. This I have already discussed. This also I have already discussed. So in short, in the nutshell, what this WAM technology is, the PMUs are deployed, the PMUs are placed at strategic location. I am using the word strategic because you need to first decide where to put the PMU, because you need to control the system. So you need to study from the controllability and observability of the system. And from the controllability and from the observability of the system, the PMUs are placed on the PMUs are placed on the systems at strategic location, and these PMUs are time synchronized. The timing signal is common. The timing signal is common means this GPS is used to give the timing signal to all the PMUs, and these PMUs take the input signal from CT and PT, and then it compute the phasors of current and voltage and also frequency, and that information, that is the current phasor, voltage phasor, and frequency information, is then given to the some control center, some load dispatch center, some state load dispatch center, or some independent operator. And to pass this, the communication backbone is used, the communication is used. The communication preferred is the fiber optic communication because the latency is very low, and time signal is time signal is common, time tag is common, and at this point, the PDC phasor data concentrator align the data containing which is having the same time signal which is received from the PMUs, and that is how it is then further processed. So yeah, this is giving a quite a good information on fiber optics based conventional current differential relay. So what we can do is that the differential relay for the transmission line you can conceive from the uh, by using the synchronized data and also the fiber optics. The time synchronization is very important because you can see that the sampling mismatch of even 1 millisecond will lead to about 80 degrees at 50 hertz. So this IS and IR are the IS and IR are the current and the current signals, and this IS and IR uh, are having a mismatch of 1 millisecond. So although they have the same magnitude, because their phase difference, this ID will flow, right? And this is a differential current which has caused because of the sampling mismatch and not because of the actual current mismatch. Yeah, so this slide is showing where to put the PMUs. So you can refer this, and the paper is published in IEEE Transaction that PMUs are to be deployed on 1/3 of the buses. So if suppose the system is of 100 bus, then it required almost 30 buses to be deployed with the PMU to make the system complete controllable and complete observable. Yeah, this is the first initiative of VAMS worldwide. It was on North America, and uh, they have used this PMUs for the monitoring, then improving the state estimation, post-fault analysis, operator informations, oscillation dampings, etc., etc. So PDC can be it can also be used for the protection. Now this PMUs, the data sampling rate is not yet for the primary protection, but they are used for the secondary, the backup protection. So what it does is that the current data, voltage data, and frequency data, the current and voltage phasors, that means magnitude and the phase angle, and the frequency data is collected at the phasor data concentrator, and this is nothing but a computer where the data is being received, and here the data is then aligned with the same control, same time tag, and then that data is then used for the phasor data visualizations or analytic functions or the data algorithm, and that is how the control and remedial actions can be taken based on this data or based on this analytic. We can also use the same slide. We can also use the VAMPs now for DMS or demand response purpose or distributed generations in the distribution system. For the transmission systems, we have certainly used it for many purposes. We have a wide area control. We have analytic. We have a substation automation. We have EMS, the dynamic security, the generators, and ISO compliance, etc. But now people are also using it for distribution purposes because a lot of distributed generations are getting connected, which are putting more complexities in the distribution system. So this slide is showing that right now we can use the synchronized measurement based technology, VAM technology, in this green area. It is still not being used for the primary protection with the PMUs. Uh, yeah, let's come to this blackout. Okay, so I will skip this many of this slide because we are aware of the Indian power systems. It's a very huge power system, right? It's a very huge power systems. The This slide is showing how much HVDC link, how much power exchanges, how many market transactions happens, and how many people are being survived, are being fed, are being served with these power systems. So it's we have really an international exchange. We have exchange with the Nepal. We have exchange with the Bhutan. We have exchange with the Bangladesh, and the day may come that we will have also exchange with the Pakistan. Yeah. So we are operating one India, one grid, one nation, and one frequency. That means the entire grid is interconnected. The last region was the southern region, which was interconnected in 2014, and in the renewables, we are fifth largest in wind, right? So it's slowly moving like towards that. These are the generating station, the powerful areas where the power generation is happening. And if you see, the load centers are somewhat at different location. So these are the generating station, these are the generating station, here hydro, here thermal, but these are the major load center. And the job of this integrated power system is to feed this major load center over the transmission network, and that is how most of this transmission line, HVDC transmission line, has come up to cater the need of these load centers which are in this particular part. In Maharashtra also, we have a power generation in this Vidarbha region, and that's why this long transmission line are laid from this to this, including the HVDC transmission line between Chandrapur to Padghe. So a lot of planning studies are required while designing the power system. And this HVDC bag has played a very important role when these five regions were interconnected, and exchange of power was through this HVDC small link, which called as the back-to-back Bhadravati, Vindhyachal, Vajuga, and Sasaram. So you can see that this is the power highway, and we are pushing the power. We are putting the generation in this highway, and we are pushing the power across the load center. Now, this is the UG student project, which was on the synchrophages measurement, and it shows that I mean, these graphs were collected. These graphs were captured by UG project of 3, 4 IITs and CUEPs, and you can see that a small frequency meter you can connect and to the computer, and computer clock you can synchronize with the global clock, maybe on the some of the clock you are receiving from the internet site and all. And then you can see the difference in the frequency of the various region, like Mumbai, Kanpur, Kharagpur, Ahmedabad, etc., which is happening because of the load generation balance. So this is the snapshot catch during the generation trip. These are the different snapshot catch, but on 2012 there was a blackout on the Indian power systems on 30th and 31st July, and you may be remembering that income tax return filing date was also extended. So that has put the systems into blackout, and this can be seen from the system frequency. So this was captured from this undergraduate project of frequency monitoring of the entire system. And you can see that this system was running with the stress situation, and here something happened, and then the system started bifurcating, and here again something happened, and then the system finally leads to collapse. So then we analyze this data with the data published in the report, post-mortem report, and you can see here that the system frequency is somewhere 49.65. That means the system was running with a stress. I mean, the load was more. And here you can see that the system is not subjected to the fault, but this major line, that is Gwalior to Bina line, was tripped on the load encroachment, and that distance relay could not identify that it was a load encroachment. It was not a fault, and this major corridor is lost, and that's why the load on that corridor shifted on some other transmission line, and it has created a swing also. So what happens that the Jamshedpur to Raurkela lines again subjected to load encroachment, and again that was again those lines were also tripped, but this Bhinmal to Sanchar lines was subjected to the power swing, and this distance relay tripped on the power swing, which we have discussed earlier in the earlier slide, and then it started further oscillating, and you can see that the system was really crying for help in this particular time, but system could not get any help. No corrective actions, no control actions was initiated, and finally the systems bifurcated. And it was God grace that the load generation balance of the western regions managed somehow, and western region could only survive. This was entirely in dark. This was entirely in dark, right? And it took time to again synchronize the systems. I think there were some 2-3 tips happened. I don't remember now, but 3-4 trips were happened, and all those things you need to play. So the point is that such in during such situation, this wide array measurement systems and the synchro phasor measurements and technologies can play a very important role. So we have just simulated the system of the western region, wherein we have the Madhya Pradesh, Gujarat, Maharashtra, Chhattisgarh, and Goa for the transient stability studies, and then we created the fault on one of the transmission line passing to Dhulia, and you can see that the system is stable in this period. But after that solid fault on at the Dhulia bus, the system has trifurcated into 3 zones. So it has trifurcated 3 coherent groups. Okay, so then I mean, if this is happening, then the only option with you is isolate the system. But this isolation of the systems cannot be at any part of time. You need to have a controlled isolation, right? The generator which wanted to maintain the coherent group, that should be allowed to work in a group, and for that you need to have a controlled controlled separation. And for this control separation also, the wide array measurement systems plays an important tool. You can get the wide array measurement, you can get the system data, and based on that you can have some analytic, and you can run where from the system is to be separated. If the load generation is not being balanced, right, then the island will not survive, right? Island will not survive. Island will again go into the tripping. I will further extend the discussions for 1 or 2 advanced protection scheme, which basically use the synchronous measurement. So we have developed enough of primer for these protections and wide area measurement and blackout. Now, distance relay is maloperation of the distance relay is the main reason for the blackout. And the point is that if that is the situation, that is the case, then why should not we go for the differential protection, even for the transmission network? And the answer is yes, we can go. Earlier, the differential protection were not used for the transmission line because there was the difficulty in time synchronizations of the data, because transmission line is quite large, quite long, and how to synchronize the sampling of 2 ends, that was the problem. How to transmit the data from one end to another, that was also a problem. And of course, during no fault condition, because of line charging current, the transmission line sending in and the receiving end difference is not zero. This can be handled, right? This can be handled. So this is what I was saying, that complexities in synchronous measurement and all. But this fiber optic technology for data communications and the global position system for time synchronization has asked the protection engineer to think on the differential protection as an option for the transmission system protection even, and that is how you could see that there are many researchers working in this area. So I have already said that this was the first attempt to use the differential protection for transmission system protection, and it's also I have, yeah. So this slide is showing that if the sampling is mismatched by 1 millisecond, then you will get 18 degrees at 50 hertz, and that will be sufficient to trigger the delay. The channel uh, the the transmission of the signal and the time delay, that is the latency, will also play important role. But if the signals are time synchronized, then we will not go for this computation of the travel time, forward travel time, or the return travel time, but we can certainly try to align the signal with the same time tag. That is what I'm saying. So there are various schemes which are being conceived with using this technology. This is the current differential scheme using uh, the the equivalent pi model. We know that let's take this as a transmission line, and this transmission line is constructed. So once the transmission line is constructed, we know its transmission line model. We know the transmission line model. The more accurate transmission line model is the equivalent pi model, and that equivalent pi model can be computed from the transmission line parameters, and the transmission line parameters can be computed from the physics of the transmission line, right? And then equivalent pi model is close to the distributed model. It's the exact model for the long transmission line. And then if you think of implementing the current differential protection, then instead of implementing the current differential protection on this current, that is line current, what you can do is that, as you know the model, you can compute the series branch current, and the series branch current, which are the fictitious current, which are not the major current, which are the computed current. On those computed current, if you implement the differential algorithm, current differential algorithm, you will get a more accurate kind of scheme, because here you are not dealing with the distributed parameters. And then you can conceive the relay, you can implement the relay in current differential plane. Unlike the normal relay, you can find out the ratio of this current, which is the magnitude of current seen from one end and current seen from second end, and then the angle difference between these two, between the current, right? So this is what you can see. So obviously in this particular case, you are getting rid of this line charging current, and this relay will certainly supersede in terms of the performance over a distance relay, and it has superseded. But the measurement has to be time synchronized, and you need to transmit the data. For transmit the data, you need a strong fiber optic network. During the fault on this line, if the fiber optic network should not fail, so you should have alternative path, sonate kind of situation, kind of architect to have a faithful and reliable fiber optic network. That is important. The scheme can be implemented on three-phase system, because you can reduce the model of equivalent pi model of the three-phase system of a transpose line. And then the scheme can be made adaptive also, because you know the restraint area can be small restraint area can be acceptable for the high resistance fault. High resistance fault will not ask you for more restraint area. Also, the larger restraint area is required for the low resistance fault. So you can. The point is that can you make this restraint area a little bit adaptive? And the answer is yes. We can make it adaptive. This is the differential. This is the restraining function which is making the resistant area adaptive, and because the height of the resistant region should be function of the current magnitude. So uh, yeah, these things are available in the publications, and work is being published available on the IEEE sites and all. If suppose we have seen that there is a problem with the series compensations like voltage inversion and current inversion, for which the distance relay maloperate. So in those situations, your synchronized measurement unit can be put after the series compensator, and again you can implement the same algorithm. But if the pair compensator is available, is deployed at the midpoint, then what you can do is that you can put the synchronized measurements here, and you can find out the model of this transmission section, also model of this transmission section, and from simple Kirchhoff's current law and voltage laws and Ohm's laws, you can find out the current in this, then current in this, then current in this, and then finally current in this. Okay, so this is the series branch current, which is again a fictitious current. You cannot measure this current. Similar exercise you can do it from this side, this current, then this current, then this current, and then this current, and you can implement. Everything can be done in a processor. Everything can be done in a processor, and then you can implement the processor. You can implement this current differential protection algorithm in the processor on this fictitious current. So this is what you can do. Similarly, you can go with the tepid line. These tepid lines are also very much there. So for tepid line, if the line model of this and line model of this and line model of this is known, then you can use the Kirchhoff's current law. You can implement the Kirchhoff's current law at this node, and then you can implement the same scheme in the same way. So yeah, so this is the equations how to compute the current at the tap position, and then how to implement the sustaining current, etc. You can go ahead with that. You can also use it for mutually coupled line, the double circuit transmission line. For double circuit transmission line, you can use it in the phase domain as well as you can use it in the model domain. So the model transformations in a double circuit transmission line facilitate for the conversion from phase quantities to the model quantities, and model quantities are completely independent, I mean completely decoupled. So for 6 current, you will have 6 model current, 6 phase current, you will have 6 model current, which are completely independent. And as they are completely independent, those model current then can be used for the relaying purpose. So you can implement the differential protection scheme not on the phase current but on the model current. That is what I am saying, and that scheme will be independent of the mutual coupling. Okay? So that is the advantage. Now these are some slides which are showing the results of these schemes. I will not go through that. This is there in the published paper, but I have just covered the basic scheme. The second scheme, similar scheme, you can conceive with the distributed parameter, distributed model of the transmission line. So the distributed model of the transmission line, this is the distributed model of the transmission line. So what you can do is that this current and voltage at one end and current and voltage at the second end are measured, and they are time synchronized. So you can take an intermediate point and you can compute the current and voltage at that intermittent point K from this end, and also you can compute the current and voltage at the intermittent point from this end. And if there is no fault in the system, then there is no reason that these two currents computed current should be different, right? So you can compute this current in the sequence domain, positive sequence, negative and zero sequence domain. There are advantages of that in terms of the accuracy and all. And all these computations you can do it in one can do it in a processor. So these are the simple equations taken from the book. This U is nothing but voltage. So this is the model of the transmission line, distributed model of the transmission line in terms of this cos h and sin h component. and this current component uses this component can be computed from the parameter of the transmission line. So 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 this is what you can do, right? This is what you can do. Now with the synchrophasor measurement, you can remove the inaccuracies in the measurements, right? You can remove uh, the inaccuracies in the model, right? Because you can expect some inaccuracies in the model from the fact that the transmission line actual conditions are not same. They may be deviated from what is being used for the computation purpose. So what one can do is that one can use the time synchronized data of both the ends of current and voltages, and that data can be used for estimating the model. Transmission line can be considered as the black box, wherein you can use those equations of the two-port network and you can compute the model of the transmission line. Uh, the above schemes were based on the phasor estimation. But if the time synchronized measurements are available, then you can take advantage of deploying more schemes, conceiving more scheme, and one such scheme is the moving window averaging scheme. This is also published in the paper. All the schemes are published in IEEE transactions. Okay, in power delivery. So the effect of DC, you know that the DC offset affect very badly on the phasor estimation, right? So phasor computations is affected. It is erroneous when the DC offset quantity is more. Also, if the system frequency is deviated, then you will get such kind of sort of waveforms in the phase angle computations, and both of this happens because of the phasor computation. So the idea is that can we take read of the phasor computations? Can we can we think of some other technique? And yes, that technique can be the moving window based averaging technique. And what in this averaging technique, what you can do is that you take this signal IS and you take this signal IR, and you find out the moving average over one cycle of this end and this end, and then you can use it for the differentiation. So that is what you can use it for the differential protection. So obviously, the signature will be there for one cycle. After one cycle, you will not have that signature because signal would have been reached to next steady state value. And but the protection decision anyway you have to take it in one cycle. Okay, so you will get such signature from this end, and you will get the similar signature from this end. If there is no fault on the transmission line, then this signature and this signature will be same. So this discriminating function will be 0. But if there is a fault, then certainly this discriminating function will be non-zero, and that non-zero discriminating function can be used for identifying the fault, right? And then again, this scheme is tested for the performance on various conditions, that is internal fault, external fault, and other disturbances, and that is how the fault that is how the more sensitive and more effective scheme can be seen. There are many schemes, but I hope with the limited this time, we cannot say limited because organizers have given me 2 hours. But because of the time constraints, I think to conclude on this, I think this wide area measurements and synchrophasors are going to play a very big role in transmission system, and not only in transmission system but in distribution system as well in times to come, in years to come. And the concept of protection systems is now shifting because you have a data at the transmission level. You have a data, and the data, huge data, can be used for transmission system protection schemes like system protection schemes, okay, adaptive protection scheme, etc. So this is what this is what we will discuss, Madam Pasmenta. This is what we will. This is what I mean the future of this future of this wide area measurement systems is very potential. These are some of the areas where we are working here in College of Engineering Pune, like phasor frequency computation, phasor computation, PMU placement, the protection, line protections, the secure backup protections, and all the parameter estimations, the system integrity protections, and blackout and islanding. And we are also working on microgrid, nanogrid, electrical vehicles, some power trans applications to the power systems and converter topology. So with this, I would like to conclude that this WAMP synchrophasors and synchronous measurements, these are putting the smartness in the grid. Of course, there are many technologies, and it's a very exciting time for the power stream protection engineer. Obviously, the field has now become more interdisciplinary, more multidisciplinary rather. And with the available technologies, one can certainly think very innovatively to deploy the new scheme. If you want to take the readings further, you can refer for the initial part, that is for the hub part, which I have presented. You can refer Professor A.M. Kulkarni and Professor S.S. Soman's NPTEL course of IIT Bombay, and this this blackout. You can refer Professor A.G. Phadke's papers, and for the protection schemes which I have presented, and some data I have presented. So for that you can refer the internet, I mean IEEE sites. Most of these schemes are presented in IEEE transactions, including PME placement and 2C protection schemes and all. And that is what I would like to conclude from my side. Thanks once again to the organizers of this FDP and the principal for having inviting me to interact with you on this day, this afternoon. Thank you very much. Thanks a lot.
I would like to request all the participants to ask any doubts or queries by raising hands, or you can ask your queries in the chat box.
Okay, I will also come online. I mean, I will also turn on my video. Yeah.
Please raise your hands. So I think nobody has a doubt.
No question.
So I would like to thank Dr. Sanjay Gambhare sir.
No question.
For being with us.
So I don't know. No, thank you very much. Nice session is okay. But any question on any of these slides or any topic, any quick questions? I know it was a long session, but it was for 2 hours, and I just closed the session at 3. So maybe we can request the organizers for a couple of minutes and couple of questions. So,
yeah, no problem, sir.
Yeah, maybe in chat box. You can see the chat box.
Yeah, you can write in chat box.
Sir, to know more about PMU, which source we can refer, sir, to motivate the younger students to work in the area of phasor measurement units? What are the books we can refer, sir?
Yeah, there is a book by Professor Phadke, Computers. I mean the numerical protections, computer-based protections, or numerical protections, and that is a book which talk of the protection, numerical protection. So I suppose that is important for us to go for that. And this Professor S.S. Soman's web course on numerical protection, that is also good. So that is a good part to start with.
Thank you, sir. Thank you.
Anybody have more queries?
And in that protection, NPTEL protection course, if you have a difficulty, you can contact Professor Soman or even to me. I was there in the course. And, also help you in some of the aspect. Yeah.
Okay.
So I would like to thank Dr. Sanjay Gamari sir for being with us today and sharing his knowledge and experience on advancement in power system protection with us. Now I would like to invite Professor Zole sir to present vote of thanks.
Thank you. On behalf of Government College of Engineering, Nagpur, GCOEN, I, Sachin Julle, Head of the Department, Electrical Engineering, take this opportunity to propose the vote of thanks to our resource person, Dr. Dambhare Sir, Professor in College of Engineering, Pune. We are really enlightened with your knowledge and presence, sir. We are really happy to attend your sessions. Thank you very much, sir, for the informative session. Thank you, sir.
Thank you very much. Thanks all the participants. And in case you wanted to discuss more, you can mail me. I have already given my mail ID, so please feel free to be in touch if you need any more information on whatever we have discussed or whatever we have gone through today. So thank you very much.
Thank you, sir.
Thank you, sir.
So I request all the participants to stay connected for the next session.